Hello everyone! Today I would like to do something a little bit different from the usual combat robot fighting clips, and do a full breakdown of the newest iteration of my Antweight undercutter combat robot called PureD. So this is the third version of PureD that I just finished, and it did not enter any competitions yet. If you're interested in the previous two versions, all of their fights are uploaded onto my YouTube channel. Now, let's get on with the breakdown. Okay, so enough introductions, let's get into the breakdown of the robot itself. So the first thing you see on PureD, and definitely one of the most standout and important components, is our large red weapon disc. So this is actually powered by a direct drive hub motor system that is shock mounted onto the chassis. We will get back to that later, but first let's take the spinner out of the robot. So it is held on by only one set screw collar. This is the one that holds the entire weapon assembly in. It's not the most optimal because the set screw collar could potentially detach, but it has yet to happen in the two tournaments I went with PureD. But a better alternative would be a clamping collar, and I'm trying to look for clamping collars that would fit onto this shaft. So with that removed, we can now take the weapon assembly off, which just vertically slides out of the robot. And here we have our spinner weapon assembly. So first, let's talk about the spinner itself, the metal part that hits other robots. So it's made of 3mm grade 5 titanium, which is the grade of titanium that people looking into combat robotics should get. So here's how it looks unpainted. This is a much stronger and stiffer grade of titanium that is an alloy with 6% aluminum and 4% vanadium, as opposed to things like grade 2 titanium, which is pure titanium. But grade 2 titanium is much softer and much weaker, so we want the grade 5 alloy titanium. This is what's strong enough to build spinners out of, and also more common and more cost effective. So how the spinner was made is using water jet cutting. So this titanium started out as a stock sheet, and then it was put into a water jet and cut in a two-dimensional pattern to the desired shape. So this is only a two-dimensional shape. There's no 3D cutting to it. It's only cut in 2 dimensions from a DXF kind of 2D image file. The other interesting thing about this specific titanium spinner, as seen here with the red, is that it is painted. So a lot of people may tell you that it is either very difficult or impossible, basically, to paint on titanium. But usually they refer to the finished titanium surface, so that is if it's finished with a polish or with a brushed surface, and that would be very, very difficult to paint on in actuality. But because the discs were just water jet cut from stock sheets, so you can see here, this is all non-finished, it's rough, and there is a really, really thick oxide layer. And with this rough oxide layer, I was able to paint on these spinners with just a spray paint. So some people would say you must anodize the titanium, but with these, this is already a big thick oxide layer on it, and you can't really achieve this type of dark red with anodized titanium. This is painted for that reason. I didn't want more of a purplish red, which is what you would get from a anodized finished. So now let's look into the motor that powers the spinner. So because it is a hub motor, you can see the rotor of the motor, which is this part. This is an outrunner motor, so the rotor is on the outside. It's the outside can that spins with the rotor, and the rotor has permanent magnets on it. Because it is a hub motor, the rotor of the motor is directly attached onto the spinner using a hub. And this is a UHMW hub that's machined on a lathe using UHMW. So you could see the rotor directly attaches onto the hub. Let me get a little bit closer. So the rotor, in here there are 3 screws. So this is a motor that's originally designed for remote controlled aircraft. It's a DYS 1100 kV brushless outrunner motor. And because it's designed for a remote controlled aircraft, it's supposed to mount onto a propeller. So these 3 screws, these 3 small screws, they originally mount the motor can onto a propeller. However, in this case, it's used to mount the motor can onto this hub. And then, from this hub, it is then mounted onto an adapter, which is aluminum, this adapter here. And then that adapter then adapts the screw pattern to the spinner's screw pattern, which is 0.77 inch spacing screw pattern, which you can see with this one here. This is the screw pattern on the spinner. It adapts from this hub screw pattern onto the spinner screw pattern. So this basically connects all of the components from the rotor of the motor, all the way to the spinner in one single piece. There's no give, and it rotates as one single piece. So that's the rotor component. And now we can look at the stator that has all the coils that actually power everything. So the stator is mounted inside the robot. It's mounted directly to the top panel. So I'm using the same mounting mechanisms that it was originally intended with to mount onto an aircraft. There are 4 screw holes on the other side of this stator that basically allows it to go onto the front of a remote control aircraft. Let me get a new motor. So this is what the motor looks like originally. You can see that the rotor comes off. This is the rotor, same as the one that goes into the hub. And then you got the stator here. This one is unprotected. The one in the robot I sealed with a little bit of epoxy to make it a little bit stronger. But there are 4 holes on the bottom that originally mounts onto an aircraft, and that's used to just mount onto the top panel. So that's it for the weapon motor. The final aspect of the spinner, that is probably the most important kind of design aspect it took, is that it is how it is stabilized onto the chassis, so all the energy of the hits are absorbed. One of the most important parts of making a successful combat robot, especially in a spinner, is to make a strong mount. This is because on every single hit, you impart energy into the opponent by hitting them, but at the same time, you impart the same amount of energy into yourself due to Newton's third law. So how the energy is absorbed by the chassis, how it not damages the chassis, is extremely important. So first of all, you could see the rotor has a metal shaft attached to it. It's the stock shaft that is fully stock from the motor. It's only been hammered in, so it's a little bit longer. And this is a hardened steel shaft, and this is only 3.125 millimeters thick. So it's usually actually insufficient for a spinner of this size. Usually on most spinners, if you use a shaft that is this size, in a 1-pound combat robot, it will bend or break. However, the design that I used prevents that from happening for at least 2 tournaments that I was in. The shaft never bent and never broken or snapped. This is because the whole spinner assembly and the stator in here, this entire stator unit, is shock mounted using a flexible nylon top panel. So I was talking about how it's shock mounted, and I also said that it mounts only onto the top panel and not onto the side of the chassis. This is because I wanted to shock mount this system. So this top panel is actually made of carbon reinforced nylon. It is semi-flexible. It doesn't flex too much, but it has enough give so that when the disc hits other robots, it would absorb some of that energy from the, and prevent all the energy from going into the shaft. So let's put this back on. And you can see on hits, there's a little bit of give. To this, little bit of give to this spinner. So this shock mounting kind of makes the entire system a lot more durable and a lot less likely to break. However, this only really works with a disc. This is extremely important, that shock mounting only really goes onto discs and not bar spinners, because bar spinners most of the time have a geometry that makes them spin on the intermediate axis instead of the axis where the highest moment of inertia is happening. So the intermediate axis is where the axis of second highest moment of inertia when spun up. And this causes the Janibekov effect, or intermediate axis theorem, to occur, which destabilizes the bar and makes it do a dance that sometimes explodes the spinner. And this is seen on heavyweight combat robots like Apex, but also smaller weight classes. And by shock mounting it, it's only making it easier. However, with a disc spins at the axis of highest moment of inertia, which then means it is actually a self-stabilizing system. It has gyroscopic stabilization when spun up. Instead of destabilizing, it actually makes the robot more stable. So this is why I can shock mount onto this top panel without worrying of it exploding or destabilizing like many bar spinners would do. And since we're already talking about the top panel, let's get into the chassis of the bot, which is all 3D printed. The top panel, as I already said, is made of nylon. It's a semi-flexible material that allows for the shock mounting to happen. And the top panel is mounted onto the main single-piece tub chassis. Here, this is all printed in one single piece. It's mounted onto the top. It's mounted onto the bottom chassis with self-tapping wood screws. So there are 1, 2, 3, 4, 5 wood screws. I found that it is most of the time unnecessary to use threaded inserts, which a lot of people use in these small weight classes. They 3D print the chassis and then they put threaded inserts to put machine screws into. However, I found it most of the time unnecessary to invest the extra weight into threaded inserts, as I found that self-tapping screws usually provide already strong enough connections due to their geometry, unless you are using TPU components. If you're printing with TPU, it's still recommended to use threaded inserts because self-tapping screws don't like to thread into TPU. So now let's take this robot apart. I could show you the top panel and the tub chassis. So after removing all 5 screws that hold the top panel in, it just lifts out of the robot, and you can see the stator is still attached onto the top panel with the screws. And now we get to see the tub chassis of the robot. So let's get the electronics out. And you can see it is 3D printed, this tub chassis here. Not the wheel guards. The wheel guards are attached separately, but the chassis itself is 3D printed in one single piece. So it is a unibody chassis. And it is printed with the motor mounts and all of the supports where all the screws go. So an interesting part about this chassis design is that it is printed using a PLA, or polylactic acid, plastic. And that raises the question, isn't PLA extremely brittle and the robot will crack when hit? While that is true for most PLAs, from some experimentation and a lot of failed cracked chassis, I found a PLA called Polymax, which fails in a much more ductile manner and is much more shock resistant. So that's what this chassis here is made of. It has the benefits of PLA, of being extremely easy to print, so that's why I really like using Polymax now to make all the chassis. It's because it's a very good combination of properties. It bridges very well, like other PLA, it has good layer adhesion, and it prints at a very low temperature, so it's easy to print on all printers. But at the same time, it has excellent, it's excellent to tap with screws. It's very strong when you tap it with self-tapping screws. And it has very high shock resistance, and it does not crack when hit. It's more comparable to ABS in terms of how it fails. It elongates and bends before it breaks, which is much more preferred on a combat robot, as it will be much more resistant to damage in a real-world situation. And attached onto the chassis, of course, there are these wheel guards. They are also made of the same PLA, and they are removable and replaceable. These protect the wheels in combat. Sometimes when the robot hits things, because it hits in a horizontal axis, it occasionally might feed the wheels into opponents, so these wheel guards are extremely important to prevent the wheels from being damaged. And sitting inside the wheel guards, of course, are the wheels and the drive system of PureD, which isn't all that impressive because all the weight went into this weapon system. This is actually 185 grams, which is a little bit less than half of the entire robot's mass. So these wheels are FingerTech foam wheels. These wheels here, they are lightweight and flexible and are made of a foam that is quite durable, but they are not very grippy. So the solution is to put silicone sealant on the surface. So you can see in this one, it's a little bit shiny because there is silicone sealant that has been applied to the surface, and that gives the wheel a lot more grip. From what I heard, liquid latex solution also works and is likely even better than this silicone sealant. But make sure to apply this often in a competition, because sometimes it sucks up dust and loses grip. So changing this silicone sealant finish often is very vital to the success. And the motors that drive the wheels, these guys here, they are N20 motors with a 30:1 gear ratio. They are not very durable at all, and I highly recommend bringing spares if you're planning to use them. However, they are very lightweight, and that's the important part because the spinner takes up all the weight. So these are not very durable, but on the flip side, they're very lightweight and they are pretty strong. However, it's advised to use these on robots that don't push all that much, like on a horizontal spinner here. This never has to go to pushing wars with other robots usually, so these motors do not have to be all that powerful. Now, let's get into the electronic components that control the motors and make everything work on PureD. Each motor in this robot, so the weapon motor and the two drive motors, each have an electronic speed controller, or ESC, to adjust the throttle on all of these motors. Because the weapon motor is a brushless motor, it has a brushless ESC, while the N20 motors, which are brushed, each have a brushed ESC. Keep in mind, when buying a brushless ESC for brushless motors, that the ESC's rating, so this one it says 20 amps, must be a little bit higher than the motor's current draw, or around the same if you're running a lighter load. But especially for combat robotics, the spinner here, this is a very big load. There's a lot of moment of inertia in the spinner, so to spin it up, it has a very high load compared to, say, a propeller. So you want to get a ESC that is rated higher than that of the motor here. The drive ESCs are FingerTech Tiny ESCs. So these are made by FingerTech specifically for robotics. They're very excellent, they're very reliable, but they're slightly on the more expensive side. Actually, without the wires, they are more, they're worth more than their weight in gold. So these are relatively expensive ESCs, but they are very excellent, reliable ESCs that are basically impossible to kill, from what I've heard from other robot heroes who build Antweight combat robots. And the weapon ESC here is a DYS 20 amp ESC, which is more than this motor will draw. And this is also a pretty reliable ESC. It's never really failed on me before. And it is proven to be quite a good ESC. The other extremely important piece of electronics is where the power for these robots come from. And these are rechargeable batteries. So this is a rechargeable battery that PureD uses to get through around 3 minutes of fighting. So it's the lower capacity configuration for PureD. But these are 3-cell lithium polymer batteries. They are ideal for combat robotics for their extremely high specific energy. So that's the amount of energy it stores per weight. So these are extremely lightweight batteries for how much energy they hold. They also have a very, very high discharge rate, which means they could discharge at a very, very high current without damage. And 3S for 3-cell, because these 3 cells you can see here are wired in series. So that gives it more voltage. In theory, this battery should give around 11.1 volts, but it gets a little bit higher when it's fully charged and a little bit lower when it's out. And voltage is extremely important in combat robots because it determines how fast your motors spin. For example, this motor here is designed with 1100 kV or 1100 RPM per volt. So for extra 1 volt this motor gets, it will spin 1100 RPM faster. So in theory, with this 11.1 volt, it should spin around 12,000 RPM. However, that's in ideal conditions when there's no drag from aerodynamics or friction from the bearings and stuff. In real life, I measured with a tachometer, the spinner goes around 8,000 RPM at full throttle. However, the reason I did not choose a battery with an even higher voltage, like a 4-cell or a 5-cell or 6-cell, is because when the motor spins too quickly, this spinner will lose bite. So when it's spinning too fast, the teeth will skip off of the opponent and not actually get any bite. So that's the reason for 11.1 volts and this choice of battery. The next piece of electronics that we are going to talk about is for safety. So for robots to enter competitions, it must also have a physical power switch that's accessible from the outside of the robot that disconnects all power to the robot physically. The power switch used here is a FingerTech switch that uses a 3.5mm headphone jack as a toggle. So when you insert the headphone jack into here, the power will be disconnected, and if you pull it out, the robot will be powered on. This is an extremely important safety feature for robots because if they are going to have a malfunction in the receiver, for example, or some sort of software malfunction, the weapon might stay on even if you tell it to turn off with the transmitter, or it might drive around uncontrollably, posing a hazard to people near the arena and people who are trying to access the arena. So this power switch here will instantly turn the robot off and neutralize any sort of hazard that this robot might pose. And lastly, there must be a way for the robot to communicate to the remote controlled transmitter. So the setup I've been using here, this receiver, is from Spectrum, and so is the transmitter. I have a DX9 9-channel transmitter and this 6-channel receiver, which I use for combat robots, but also I used to use this for remote controlled aircraft. It's a little bit excessive right now for combat robotics. As you can see, it has 6 channels, so 6 ports here, but I'm only using 3 because most combat robots only use 3 channels. So the 3 channels, each one of them are the weapon, which connects to the weapon ESC, and the 2 drive channels, which both connect to the two drive ESCs. And how they are wired is the throttle goes, so the weapon ESC goes into the throttle channel. So this is originally meant for aircraft. Throttle channel goes to weapon, so the throttle will control the weapon, and then the elevator and aileron channels are what goes into the two drive ESCs. These two channels are then mixed in the transmitter with a what is called an elevon mix, which is also used for aircraft, but it basically makes the two channels, the aileron and elevator channel, work in unison, which allows these motors to, power up and drive forward, back, and turn left and right. And this is all done with the transmitter. So you wire these with aileron, elevator, and then you set an elevon mix on the transmitter. And that's it for my breakdown. If you're interested to see how PureD performed in the past, please check out my fights on my channel. And I hope this video was of help to you, and thanks for watching.